Okay, so we are called this lecture 24, and we are working POGIL exercise 11A, which is page 125, and this is called electrophilic addition. Okay, so as always, you start working the Model 1 questions, and I will too. Two, three, four, five, six. Okay. One A. Consider the reaction shown in Model 1. How many compounds are present on the reactant side of the equation? So on the reactant side, did you put 2? So we have 2 compounds. Okay. 1B. How many compounds are present on the product side? Did you say 1 on the product side? 1 compound? Okay, 2. Describe any changes that occur in the reaction. So what, on the reactant side, what bonds are being broken? The carbon-carbon pi bond. So the carbon-carbon pi bond here is being broken. And so is the chlorine-chlorine bond, sigma bond. Okay, so that's broken on the reactant side. On the product side, what bonds are being formed? Carbon Cl bonds. So 2 carbon Cl bonds are formed. So 2 bonds are broken, 2 bonds are formed. Okay, so if you put in words, can you say that maybe Cl has added across the pi bond? Okay, so that's the net reaction. That's really 3, right? What is the net reaction that best describes the net reaction? Would you do substitution, elimination, or addition? Did you circle addition? Okay, so let's do 4, question number 4. Classify the following as substitution, elimination, or addition. All right, so we have, this is a ketone, and we have hydrogen. And what would you call that? That's addition. We have a secondary alkyl halide. What is that? The Br has been replaced by the Cn, right? Did you write substitution? Okay, what about C? This is organic too. This one you will see. Here, let me show you something. Sometimes you want to draw in all your bonds to see it. So if you do that, you might be able to see this a little bit better. What would you call this? Substitution. You replace the H with the Br. And then D. And that's an alkene, so we'll be doing these reactions in this chapter. Okay, that would be addition. Okay, so that has been replaced by H. You got your H there, and your Br one here. All right, so this is electrophilic addition. So we're going to be adding reagents. So hopefully what you got from this model 1 is we're going to be adding our reagents to our alkene pi bond. And so two things are going to come together to make one. And we're going to do addition. Okay, model 2. This is possible mechanism for addition reactions. Transition state 1, intermediate, that's in the valley, right? This is step 2. In step 2, we have the transition state. Because you have at the second peak. And so Cl has added here. H is added here. And this is step 2, which should be over the reaction arrow. All right, and this is stepwise. See how we have step 1, step 2, and then we could also have concerted. So we're not going to have an intermediate. And you just have a transition state. And you only have one. And when you do this, not shown on there, but you have to show that you've added, you got to show your stereochemistry. Okay, so I'll put that on there. What's happening is here you have these electrons are adding there, and these electrons are adding there at the same time, and that's concerted. All right, so now we're ready to answer questions. Consider the stepwise mechanism in Model 1. Model 2, how many steps are in the stepwise mechanism? So you have step 1 and step 2. So what did you write? 2 steps? Okay, what role does the alkene play when it reacts with HCl? Okay, you see how those electrons are going to the hydrogen? Okay, it is a nucleophile. What intermediate is formed after step 1? So what's this intermediate? What's that intermediate called? Carbocation. Okay, it's a carbocation. D. What role does the intermediate play when it reacts with the chloride? Okay, now it is an electrophile. Okay, so it started out as a nucleophile in step 1, and now our carbon substrate is an electrophile in step 2. So you see how the chloride nucleophile will add to the carbocation. Curved arrows are illustrated for the stepwise mechanism. What do the curved arrows represent? So you write movement of electron flow from nucleophile to electrophile. Okay, 6. Consider the concerted mechanism. Okay, so now we're looking at the concerted mechanism. How many steps are in the concerted mechanism? Did you put 1 step? Is the intermediate cation formed in the concerted mechanism? No, we have no intermediate, no carbocation. Compare the products for the concerted and stepwise mechanism. The products for both mechanisms are, they would be considered the same. That's what they want here. Draw curved arrows to illustrate electron movement for the concerted mechanism. And that's what I did here with the red. So you have, these are adding at the same time. As a group, discuss whether the mechanism for addition to an alkene would be concerted or stepwise, or if there's not enough information to determine. At this point, your mechanisms would be determined experimentally. Okay, so you're going to find that some reaction mechanisms are stepwise and some are concerted. And there's no way for you to know. You would have, these experiments have to be done in the lab, and then we're given the data. And that is why we have to go through each one of these reactions, and it is summarized for you in this textbook to tell you this is a concerted mechanism, this is a stepwise mechanism. So that's why you have to study these and do this, because we're talking 30 and 40 years of someone's life working in the laboratory to be able to say this is a concerted mechanism. The reason why it's important is if you're trying to synthesize a molecule, which I have done for cancer drugs and new molecules, sometimes you need to have that stereochemistry where both hydrogens are added on the same side of the bond, because the shape matters. And so you need to know, oh, I can use this reaction. Oh, I want a Markovnikov reaction, so I can use this one. So that's how how important it is for application. Okay, model 3. We're going to, this is our first reaction here, addition of HCl. And I did talk about this, HBr, which HCl or any kind of halogenation in the previous lecture. Okay, so let's see what Pogel has to say. Okay, so we are adding HCl. This is equation 1. And then we have this. And a Br. Equation 2. All right. So questions. 8a. In equation 1, model 3, the alkene is reacted with HCl only. Okay, so it's reacted with HCl only. What product is formed? What are we going to call that? Alkyl chloride? The alkyl chloride. we can actually give it its name. So let's number it. 1, 2, 3, 4. So 2-chloro dash 2, 3 dimethyl butane. Okay, what you got? Okay. B. In equation 2, model 3, the alkene is reacted with HCl and sodium bromide. So you probably put some sodium bromide salt. What products are formed? So we have alkyl chloride and alkyl bromide. We have the one here, and then we can also say we have 2-bromo-2,3 dimethyl butane. All right, C. Describe what is different between equation 1 and equation 2. Well, in equation 2, we also have a source of bromide ions, okay, because you're adding sodium bromide. Okay. In your groups, number 9, discuss whether the outcome from equation 1 helps determine which mechanism. You think it's stepwise or concerted? Yes, I agree, stepwise. And let's see if we're going to see that. Stepwise, because the first one, let's look at the first reaction. You get 2 electron flow arrows, and the hydrogen adds here, and then you're going to get this as a carbocation, okay? And then that's where you could have the chloride act as a nucleophile to electrophile, or if you have a source of bromide, the bromide could add. So yes, you're going to get stepwise. Consider the two products formed in reaction. This is problem number 10. Discuss whether the stepwise or concerted mechanism best explains the formation of these two products. Once consensus is obtained, explain your mechanistic choice. So this is what we decided, right? That step 1, we add the proton, and then step 2, the nucleophile adds to the carbocation. All right, now we're at 11. In determining how to draw a reaction mechanism, it is helpful to identify the roles of the reagents and to proceed one step at a time, using curved arrows to show the electron movement for every bond broken and formed. In the reaction of the alkene with HCl, HCl acts as what? Do you circle acid? Yes, so HCl is acting as an acid. It's donating the proton. HCl acts as an acid, and then you would circle accepts. So the H is accepting the electron pair. So the electron pair is this pair right here. So those 2 electrons are forming the bond. So the H is accepting those electrons. The alkene, so here's your alkene, acts as a base, okay, and it's going to donate those electrons. So the first step of the stepwise addition of the proton to the alkene is shown below. Label the reagents as acid and base and draw the curved arrows to indicate the electron movement. Okay. So let's draw that. Can you do that? All right, so the electrons go from the alkene here, and then we have to add that. Let's make this blue. Those electrons go there. This would be the acid, and this would be the base. You did this in acid base. Okay, number 12. Draw the complete stepwise mechanism using curved arrows to explain the formation of the two products in this mechanism. You will have to draw these mechanisms, and that means electron flow arrows. Okay, so the first thing that happens is the nucleophile. Okay, so this is your nucleophile, goes after your electrophile. And those electrons then are given to the chlorine. And you make your more stable carbocation. So H will add, making your carbocation here, and then you generate a nucleophile. This is step 1. Form the most stable carbocation. And then step 2, the nucleophile adds to the carbocation. And that's how we have done electrophilic addition. Also on here we have the bromide. So what if we have bromide? Because you have a source of bromide with the sodium bromide. And then this would add. So you already have your hydrogen that's added there. And that's how you get your bromide. Okay, we are on our last model for this section, Model 4. This is addition to unsymmetrical alkenes. This is where we're going to talk about Markovnikov versus anti-Markovnikov. Okay. Hold on. Okay, so we're going to talk about Markovnikov and anti-Markovnikov. So let's go ahead and get this model down. Now, if you look at the other models, the starting alkene was symmetrical. This one's different. What does that mean? Well, it means that of the two carbons that make up the carbon-carbon double bond, they have different numbers of substituents. Okay, so we have this box here, carbocation intermediate. Then we have this box here for the carbocation intermediate. And then this shows you that 1, 2, 3. Call that B. I'm calling this A. All right, and we call that C. Let's answer our question 13A. In structure A for model 4, compare the two carbons of the alkene, carbon 1, 2, 3, 4. So they're saying compare carbon 2 and carbon 3. How many R groups are on carbon 2? So carbon 2 has 2 R groups. How many R groups are in carbon 3? Carbon 3 has 1 R group. Okay, 13B. Structure A is considered to be an unsymmetrical alkene. Explain why. Because the carbon-carbon double bond each carbon has a different number of carbons attached. Okay. So C, 13C. When HCl is added to compound A, here's HCl, it's added to compound A, two possible products B and C are formed. B and C. For product B, which carbon did the hydrogen from HCl add to? So it added to number 3, right? For product C, which carbon did it add to? Circle carbon number 2. Okay, now we're on 14. Given that a stepwise mechanism of addition takes place, draw the carbocation intermediate in the box above that would result in product B, and the intermediate that would result in product C, and then label them as either primary, secondary, or tertiary carbocations. All right, so if we had the first one, we have the H adding here. That would make your carbocation on the 2. And that would be a tertiary carbocation. If we had this product here, and we have the hydrogen adding to carbon 2, then we would get the carbocation on carbon number 3, and that would be a secondary carbocation. Once your group, well, let's see, which cation would be most likely to be formed? Which one do you think? Yeah, the most likely to form would be the tertiary because it's more stable. Only one of the products, B or C, is formed. Based on your answer for 14B, put an X to the product that does not form. Did you put an X through C? That's right, C doesn't form. So your major product is B. That's regiochemistry. Once your group has agreed which product will be formed, draw curved arrows in Model 4 to show electron movement. Okay, so you would show the first thing in step 1 is this is step 1 to form the carbocation, and then you would get Cl minus, and that nucleophile then would have, and that would be for step 2. All right, number 15. 15, Markovnikov's rule. Okay, so what's Markovnikov's rule say? In electrophilic addition reaction, the hydrogen adds to the carbon of the alkene that has the most hydrogen. Which product from Model 4 is Markovnikov's rule? Okay, so this carbon has the most hydrogen, and Markovnikov's rule says the hydrogen is going to add to the carbon that has the most hydrogens. So which product of Model 4 is Markovnikov's product? Yes, this is Markovnikov. Markovnikov's. The first one, which is product B. Markovnikov's rule. If the electrophile is not hydrogen, would you expect Markovnikov's rule to be followed? Still, yes. Anytime you're generating a carbocation intermediate, then it needs to follow Markovnikov's rule. You can just abbreviate Mark's rule. Okay. Once your group has agreed with the above questions, rewrite Markovnikov's rule using the terms such as electrophile and carbocation. So what would you write? I think Mark's rule produces a product that reacts with an electrophile that generates the most stable carbocation. All right, so maybe do some of the reflection if you want. It looks like your additional questions, 16A, you need to show the mechanism. So you need to show step 1 and step 2. Keep in mind, when I'm looking at this, I'm seeing the most stable carbocation, so be sure to do a carbocation test because you have step 1 and step 2. That's what it's talking about in 16. And 17 is talking about your solvent. So keep in mind you're generating a carbocation, so what kind of solvent would you need? Maybe give some examples. 18, you're actually doing a reaction. Yeah, that's, I'll do 18 for you, so you don't have to do 18. The reason why I want to do this one for you is because we haven't really done with polymers, and that can be confusing, even though they're not hard reactions. They're just a little different. And I don't want you necessarily to be confused on your own at home. So you don't have to do 18, okay? This is number 18 on your additional, but I will show you. So this is sulfuric acid. So you're going to do this, right? And this is going to become HSO4 minus, and you're going to generate a carbocation. Now this is a symmetrical alkene, so it doesn't really matter. You can just put that there, and then you get your carbocation. Well, that reacts with itself. Okay, so then you have another one here, alkene, and this is a cationic mechanism. So you'll study polymers, and they can do anionic mechanisms, cationic mechanisms, and so here what happens then is it just keeps getting growing, and it can, so this is a gas, acetylene. Well, it's not really acetylene, it's ethylene gas. And what happens is these polymers keep growing so much that they can become solids. Okay, and so all your different polymers and your synthetic fibers, they just get larger and larger and higher molecular weights, and because they keep reacting with themselves. So then this would react again, and the molecular weight gets so big that it actually becomes a solid. So it can go from a gas to a solid molecule. And that is polyethylene. So if you've ever touched polyethylene polymer, this is how it is made, just with some sulfuric acid and ethene gas. All right, so basically you just have questions 16 and 17 for that 11A POGIL exercise.